Hi there, Mr. Holcomb here with another episode of The Math Behind the Modules. This is Lesson 12, Choice of Unit. Okay, so in this exercise what we're going to be doing is determining what unit of measurement we should use to make something understandable in our minds. Okay, so I'll explain that with exercise 1. It says a certain brand of MP3 player will display how long it will take to play through its entire music library. If the maximum number of songs the MP3 player can hold is 1,000 and the average song length is 4 minutes, would you want the time to be displayed in terms of seconds, minutes, hours, days, years? They only gave us seconds, days, or years worth of music, but we're going to explain this. So let's just assume that this thing is full and we have 4 minutes per song and it can hold 1,000 songs. Well, just for starters, we have to take that 1,000 and multiply it by 4 and get 4,000. Okay? So the number of songs an MP3 player can hold is 1,000 and they're 4 minutes apiece. That is 4,000 minutes of music. Now, this is what they're talking about when they say choosing the correct unit. Okay, let's choose the right unit here. I can't get my head around 4,000 minutes. I can't say, oh, well, a class is 90 minutes, so that would be the same amount of music as, and then have to do the division, and how many times will 90 go into 4,000 and determine how many class lengths this would be. So rather than trying to have to do mental math, we want to get it down to something that we are used to using as units of measure. So what we need to know is there are 60 minutes in 1 hour. Okay? And there are 24 hours equal 1 day. And we can keep going and going. 1 day, or 7 days in a week, 52 weeks in a year, 10 years in a decade, 100 years in a century, and so on and so forth. I could go backwards and say there are 60 seconds in a minute, and so forth. Okay? So right now we have 4,000 minutes, and I can't really get an idea as to how long that really is. So I want to convert that. So I'm going to take 4,000 minutes of music. I'm going to say 4,000 minutes, and I'm going to divide that, and there are 60 minutes in an hour, and I'm going to divide that by 60 minutes per hour. Okay, there are 60 minutes per hour, 4,000 minutes of music. And when I do that, the unit of measurement will cancel. A minute divided by a minute is canceled. And I'm going to reduce these zeros, and 6 goes into 40 6 times. 6 times 6 is 36, a remainder of 4. And 6 times 6 is 36, with a remainder of 4, and so on, and so on, and so on. So my answer is 66 2/3. I didn't need a dot there. Okay, so 66.66 repeating is 66 2/3 hours. Okay, so if the minutes cancel, actually instead of using the word per, I could use a line. So the minutes cancel, I'm left with hours. So 66 2/3 hours. I can kind of get an idea as to how long that is, but I still want to convert that down. And then we want to focus on this 2/3 here. And 2/3 of an hour, if you know that there are 60 minutes in an hour, 2/3 of 60 is 20 minutes. Is 1/3, I'm sorry, 2 times 2 is 4, 40 minutes. Okay? So 2/3 of an hour is 40 minutes. 20, 40, 60. 20, 40, 2/3 of 60 is 40. So this is 66 hours and 40 minutes. Okay, I still want to do a little bit more calculation than that. So before I go on to this, but I just wanted to explain to you that you should be able to do that as well. It could be a question like on an SAT or something. 66 2/3 hours. If I want to reduce that even more, then I can divide it by 24 hours per day, and then the hours cancel, and 66 2/3 divided by 24. So I'm going to go 66 point, and I'm just going to repeat this till it goes to the next line, and then it will round, so it'll do that, and I'm going to divide that by 24, and the answer is 2.7 repeating, which is 2.7 days. Okay, now I can also do that 0.77 and determine how many hours that is. So if I do 0.7 repeating, like this is, okay, and I know that that is a portion times 24, then I can determine how many hours that is, 18 hours. So I can break this right down to 2 days, okay, 2 days is here. The 0.7 repeating is 18.26667, which is 18 2/3 hours. I've already told you 2/3 of an hour is 40 minutes. So I got this right down to 2 days, 18 hours, and 40 minutes. Okay? So I got a little bit more specific than what the question asked, but there's nothing wrong with that. This will also prepare you for SAT type questions if there's some conversions of minutes from fraction to actual minutes or so forth. So 2 days, 18 hours, and 40 minutes is the unit of measurement I could use. So really it got down to the days here. I didn't use seconds. Okay, 2 days, 18 hours, 40 minutes. I was a little bit more specific, but if we just did it in days, it's 2.7 days. You can get an idea as to what that is, 2.7 days. Okay, exercise 2. You have been asked to make frosted cupcakes to sell at school fundraiser. Each frosted cupcake contains about 20 grams of sugar. Bake sale coordinators expect 500 people will attend, and they assume that everyone who attends will buy a cupcake. Does it make sense to buy sugar in grams, pounds, or tons? Explain. Okay, so if I have 500 people and they're all going to buy one cupcake, and every cupcake has 20 grams of sugar, then it's going to be 500 times 20, and that is 10,000 grams. Okay, now if I go to the grocery store and I'm looking for a bag of sugar, and I look at the content, they are not going to be in grams. I'm not going to buy 10,000 grams. So I need to convert this. So just without doing any calculations, I'm assuming that we're going to use pounds, because a ton, 1 ton equals 2,000 pounds. I don't think we need 2,000 pounds of sugar to make 500 cupcakes. It's just not required. So I'm assuming it would be pounds, but let's take this a little step further and let's determine how many grams there are in a pound. So I'm going to go to Google and see. Okay, so here we have it. There is approximately 450, well, no, approximate. There's 453.592 grams in a pound. So let's just say 454. Let's just round it down to 450 to make it easier, just to get an idea. So if there are 450 grams per pound, so I'm going to take 10,000 grams and divide by 450, and that is grams per pound, and the grams cancel. Then I'm going to take 10,000 divided by 450, or 1,000 divided by 45. Okay, 1,000 divided by 45, and that's going to be 22.2 repeating. 22.2 pounds of sugar. Okay? Okay, exercise 3. The seafloor spreads at a rate of approximately 10 centimeters per year. Okay, so let me stop right there. And if you have never heard about this, then let's take a look at it. Let's totally understand the problems we're working with. And we can always Google stuff to see what they're talking about and make this a little bit more interesting. So they're talking about the seafloor spreading. And you're probably like, well, what do you mean seafloor spreading? So if you Google that, it says seafloor spreading is a process that occurs at mid-ocean ridges where new oceanic crust is formed through volcanic activity and then gradually moves away from the ridge. Seafloor spreading helps explain continental drift in the theory of plate tectonics. So if I look at this closer, these red lines right here are where the seafloor is spreading. Okay, so this is where there's volcanic activity. That is actually heat. Okay. Or maybe not. Age. Oh, that's their age. So that it's younger there. Okay, red is the youngest. 0 to 10. Age of oceanic lithosphere. Up to 280. But it doesn't say. Oh, millions of years. There it is right there. 280 million years old. So right here, 280 million years, and going all the way over to this plate here is closer to 0 to 10 million years. So this line right here is where this is occurring. That's what they're talking about, these lines. And then also over in the Pacific. Okay, so that is what they're talking about when they're talking about seafloor spreading. Okay, so they're saying that it spreads at a rate of approximately 10 centimeters per year. If you were to collect data on the spread of the seafloor each week, which unit should you use to record your data? So, 1 year equals 52 weeks. So 10 centimeters. I wouldn't want to use centimeters because 52 weeks, divide 10 by 52. So if I put 10 cm, 10 centimeters, and I divide that by 52 weeks per year, then I'm going to find out how many centimeters per week. Okay? So if I have 10 centimeters per year, and I have 52 weeks in a year, then the years cancel, and I get 10 divided by 52 centimeters per week. So if I do that, 10 divided by 52 is 0.1923. 0.1923 centimeters per week. So I don't want to use centimeters because I don't know what 0.1 centimeters is, but I do know that there are 10 millimeters in 1 centimeter and 100 centimeters in a meter, and so forth. So centimeters is too big, so I want to go down and reduce that. So I'm going to divide that by 10 millimeters per centimeter, and then the centimeters cancel, and dividing by 10 is going to move the decimal over, and that's going to be 1.923 millimeters per week. And that I can measure on a tape measure. So if I go up here to my measuring device and I bring in my ruler, let me just bring this down and explain this in detail. Okay. Here is a ruler. This is 1 centimeter. I don't know what 0.1923 centimeters is, but I do know that dividing that by 10 millimeters per centimeter, that is 1.923 millimeters. So it's right about this distance right here, not quite 2 millimeters. And that's how much the earth or the surface of the floor in the oceans spreads per week. Okay. Okay, on to another interesting topic. The Giga electron volt, GeV divided by c squared, is what particle physicists use as the unit of mass. So 1 giga electron volt equals 1.783 times 10 to the negative 27 kilograms. And the mass of one proton is 1.672622 times 10 to the negative 27 kilograms. Very, 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 very small as far as mass. Okay, so exercise 4 says to show that the mass of a proton is equal to this. So we want to show that that equals that portion of a giga electron volt. So I first want to let x equal the number of giga electron volts. So it's easier to write that instead of all that word. Okay. So we want x to represent the number of giga electron volts that are equal to the mass of a proton. That's the first thing we want to do. So now that we have represented a variable x, and it is a giga electron volt that is equal to the mass of a proton, then we would say that that number times that giga electron volt equals the mass of proton. Okay, and now the giga electron volt is this value right here. So now it's just a substitution problem. So let me do that in red. So now I'm going to say x, okay, the number of giga electron volts we need, times 1 giga electron volt, which is 1.783 times 10 to the negative 27 kilograms, okay, equals the mass of a proton. And the mass of the proton is right here. And I'll do that in purple. This is the mass of the proton. And that is 1.672622 times 10 to the negative 27 kilograms. Now, in order to solve for x, I need to get x by itself. That's multiplication. I have an equal sign. In order to get rid of something that's being multiplied, we have to divide. So it's 1.783 times 10 to the negative 27. What you do to one side, you have to do to the other. Okay, I didn't really need those parentheses, but it doesn't matter, but I'll take them out. Let me put a 7 back there. And here. Really doesn't matter, but anyhow. Okay. So giga electron volt, and that is a 27, and that's a 27. Okay, so what we really want to do is divide 1.672622 by 1.783 and multiply that by 10 to the negative 27 over 10 to the negative 27. Okay, so now when I do that, okay, so when I divided 1.6726, that's a 6, 22 by 1.783, then I get 0.938. Let's just round it to there because then there's a 0. So that's approximately 0.938 times 10. And the rule when dividing means to subtract, so it's negative 27 minus a negative 27, which means plus, and that's going to come out to be 10 to the, or 27 plus, negative 27 plus 27, which is 0.938 times 10 to the 0, which is just 1. So this all goes away, and so the answer is approximately 0.938. So not quite 1. Okay, which is 0.938, and there it is, 0.938, 0.938. So we just showed that this is true. A proton is 0.938 giga electrovolts. Okay. In popular science writing, a commonly used unit is the light year, or the distance light travels in 1 year. Note, 1 year is defined as 365.25 days. Figuring in leap year every 4 years gives us an additional day in February. 1 light year equals this big number here in kilometers, which is approximately 9.46073 times 10 to the 12th power kilometers. Okay, exercise 5 says the distance of the nearest star, Proxima Centauri, is to the sun is approximately 4.013336473 times 10 to the 13 kilometers. Show that Proxima Centauri is 4.2421 light years from the sun. Okay, so we're going to do the same thing as we did last, and so we're given the distance. So again, we're going to let x represent a number of light years. This time we're going to let x equal number of light years Proxima Centauri is from the sun. Proxima Centauri is from the sun. That's what our x is. So now we're going to say Proxima Centauri, which is 9.4607. That's a light year. So what we're asking is how many light years that's what this says, light year, number of light years. So how many light years, and that's a light year, is equal to the distance Proxima Centauri is from the sun, which is 4.2421 light years from the sun. Okay, grab the wrong amount of data here. That's this here. I don't want this number here. I want that equal to this number. It says the distance of the nearest star to the sun is this many light years. Show that Proxima Centauri is this many light years from the sun. So this many light years from the sun, this is a light year. I should have 4.013336473 times 10 to the 13th over here. So there are a certain number of light years that is the distance to Proxima Centauri, and that's what we have here. This is a multiplication problem, so to solve it, to get x by itself, we're going to divide by 9.46073 times 10 to the 12th power. And what you do to one side, you must do to the other. And this is going to equal 4.013336473 divided by, wrote too fast, 6473 divided by 9.46073 times 10 to the 13 over 10 to the 12, separating our number from our magnitude of 10. So now when I divide that, okay, so when I divide that, 4.01 divided by 9.46, I get 0.42421. So I'm going to put this equals 0.42421 times 10 to the 13 minus 12. Our rule says to subtract when dividing. So that's going to equal 0.42421 times 10 to the 1. And that 10 to the 1 tells me to move the decimal one place to the right. So that equals 4.2421 light years. And what were we trying to do? We were trying to prove that number. And there it is. Okay. Exploratory challenge. Suppose you are researching atomic diameters and find that credible sources provided the diameters of 5 different atoms as shown in the table below. 1 times 10 to the negative 8 and so forth. All measurements are in centimeters. Okay, so this exercise here is just trying to determine what our measurement we should use. What measurement should we use? What new unit might you introduce? So when they're talking about unit, they're talking about the base of 10 to a power, the magnitude. I cannot represent all of these numbers using different values because I can't add and subtract values when the magnitude is different. So we want them all the same. So what one would you use? There's many different ways of looking at it. No way is wrong. But if I looked at this, I see a 12 as the greatest, an 8 as the smallest, and there's 2 of them, and an 11 and a 10. I'm kind of an average type person, so I prefer averages or central tendencies, so I'm going to use 10 to the negative 10. So if I said the new measurement would be 10 to the negative 10, what that means is it says name your unit and explain why you chose it. So it says what new unit might you introduce in order to discuss different diameter measurements. I would use 10 to the negative 10, which would mean move this decimal 2 places to the left, move this place 2 places to the right, 2 places to the left, this one's okay, and move this one 1 place to the left. Okay, so it says name your unit and explain why you chose it. Okay, so I would choose a unit of measurement. All measures are in centimeters. So I would choose 10 to the negative 10, like I said, but you could use any other one that's here. So once I name my unit, then I would have to represent it with a letter. For example, I could say, let x equal 10 to the negative 10. And then exercise 8 says, using the unit you have defined, rewrite the 5 diameter measurements. Okay, so let me just do something here so I don't have to keep scrolling. Okay, so now that I've copied this down so I don't have to keep scrolling back and forth, I need to change all these. So 1 times 10 to the negative 8, I'm just going to do this once to explain it again, is putting a 1 here, and the decimal in 1 is right here, and I need to move it 8 places to the left. So if it's here, 1 would be here, 2, 3, 4, 5, 6, 7, 8. So it was here, 1, 2, 3, 4, 5, 6, 7, 8 would put it here. So it would be 0.000000001 is what 1 times 10 to the negative 8 is. Now if I want to make it 10 to the negative 10, so now if I say it's something times 10 to the negative 10, that means I've got to move it 2 more decimal places to the left to go 9 and 10. Okay, so in order to do that, I'd have to go over 1 and over another. So the answer, the new number is going to be 0.01 times 10 to the negative 10. And that's what I'm trying to get here. In order to do this one, I need to go the other direction. I need to make, actually I went the wrong way here. 10 to the negative 8 to 10 to the negative 10 is, let's see. Okay. Food for thought there for a second. I had to take a second and think about this. Let me get rid of this. I want to make this times 10 to the negative 10. I do not want to go that direction. So if I want to start with 1 times 10 to the negative 8, it's moving to the left. A negative 8 moves it to the left. I want to go to the right 2 decimal places. So if I go to the negative 10, I've got to move 2 places more. So that would be 100 times 10 to the negative 10. And let me show you that with a calculator. So here I have 1 times 10 to the negative 8, which is 1e to the negative 8, which means times 10 to the negative 8. And 100 times 10 to the negative 10 is the same. Okay, so I do want 100 times 10 to the negative 10. but my x is going to be 10 to the negative 10, so now I can just rewrite that as 100x. Okay? Now let's do the next one. This one here. So this is 1 times 10 to the negative 12, and I need to make that times 10 to the negative 10, which is bigger by two numbers. We're getting closer to 0. Negative 12 is less than negative 10. So I'm going to move it in the other direction. So it's going to start here, and it's going to go 2 places to get to here. So it is going to be 0.01 times 10 to the negative 10. And that would simply be 0.01. And now I called this x, but it looks like the times in my... So let's call it y. It looks like the times in my 10, and it looks like I'm just dropping this. I don't want to confuse you. So if I now say that y equals 10 to the negative 10, then this is 100y. This is 0.01y. Okay. This one is a negative 8, and I want to make it negative 10. Well, it's the same thing as here. I've got to move the decimal 2 places to the right. 5 2 places to the right. I'm just going to speed this up now. Is 500 times 10 to the negative 10, and my 10 to the negative 10 is y, so this would be 500y, this one here. And then this one is negative 10, so I don't need to change this. That is going to stay 5 times 10 to the negative 10, or 5y. And this is an 11, so I have to take 5.29 times 10 to the negative 11, and I want to make it times 10 to the negative 10, which is greater, so I move my decimal to the right. So it's going to be, or to the left, just like this 8 here. 8 went up to 10, 12 went down to 10, so it moved left. As the value decreases, the number increases. As the exponent increases, the number decreases, moving to the left. So this is going to be 0.529 times 10 to the negative 10, which would be 0.529y. Okay. That is the end of Lesson 12. Go to your problem set.